All right, so in this problem we have a triangular plate, and we're told that the moment about the x-axis is 820 Newton meters, and we're asked for the tension in the cable as well as what will be the moment about the z-axis. And to do this, what we're going to do is we're going to compute the moment about the origin. So if we compute the moment about the origin, then that's going to be equal to a moment arm cross with our force, and the components of that moment are going to give us the moments about the x, y, and z axes, which will give us the information that we need to solve the problem. So all we have to do is define these different vectors and then evaluate the cross product. Let's start with the moment arm. So to do the moment arm, what we want to do is we want to pick the most efficient moment arm that we can pick. So we want to define the moment arm that's the most efficient. And so we can either define the moment arm from the origin. It has to be defined from the origin because we're computing the moment about the origin. So it can either be defined from the origin to point A, which would have two non-zero components, or it could be defined from the origin to point C, because the moment arm can be from any point that we want to compute the origin about to any point on the line of action of the force. So in this case, it has to be from O, but it could go to any point along the line defined by AC. And looking at this, we see that from the origin to point C is just going to be equal to the distance of B in the y direction, and B is equal to 13 centimeters. Now, a common mistake is to get the units mixed up. Since we have the units of the moment given in Newton meters, we have to use meters here. So we'll have the moment arm as being 0.138 meters along the J direction. And that does the moment arm. The next thing to do is the force. So our force is going to be given by the magnitude of the force, which we don't know, that's T, multiplied by the direction of the force, and the direction of the force can be given to us by the position vector from point C to point A divided by its length, which will make a unit vector. Now, another common mistake is to get the direction of the force wrong. Cables, ropes have to pull, meaning that at point C, the tension is going to be pulling, let's call this F, is going to be pulling on point C. So it has to be an arrow going from C to point A. And so if we think of this, well, to go from C to A, in the x direction, we're going to go negative A. And A is 9.4 centimeters. And then in the y direction, we have to go negative B, and that's 13, so this is 9.4i minus 13.8j, and then in z, we're going to go positive h, and h is 3.3k. Now you might wonder, well, wait a minute, why am I doing centimeters when I had to do meters before? Because we're going to divide by the length of this vector. And so if I do meters on the top and meters on the bottom, or centimeters on the top and centimeters on the bottom, or any other unit on the top and any other unit on the bottom, they're going to cancel out anyways. So I might as well stick to something that's a little easier to write. And so here I'm going to have 9.4 squared plus 13.8 squared plus 3.3 squared, and all of that to the 1/2 power. So now we'll pull out the calculator and evaluate this. So 9.4 squared and 13.8 squared and 3.3 squared, add those up, I get 289.69. Take the square root of that, I get 17.02. So we'll just write that out. So I'm going to get my tension multiplied by minus 9.4 over 17. We'll just round it at 17.0 for now. And I, give myself a little more space here, and then we'll have minus 13.8 divided by 17j, and 3.3 divided by 17k, and there we go. And so now we have all the vectors we need, and we can just go ahead and take our cross product. So our moment is going to be equal to T multiplied by 0.138 multiplied by 9.4, that's negative, j cross I, that will be k, divided by 17, we don't want to forget that. And then the next term is going to be minus 0.138 multiplied by 13.8 divided by 17. And then we're going to have, also a t, and then we're going to have j cross j, which is just going to be 0, because those are parallel to each other. I shouldn't have even had to write that. And then the last term will be 0.138 multiplied by 3.3 divided by 17, j cross k, and that's going to be I. So let's see, and also we have t here. All right, so we have all our t's, there we go. And so now all that's left is to work this out. So we can say that our x component is just going to be whatever is the I term. So we look at this. J cross I is going to be minus k, and j cross k is I. So our x component of our moment is going to be equal to t multiplied by 0.138 multiplied by 3.3 divided by 17. And our z component is going to be equal to, the negative signs cancel out, and we get t multiplied by 0.138 multiplied by 3.3 divided by 17. Sorry, copied the wrong thing. 9.4 divided by 17. And we go back up to the top. So we're given the x-axis. So this one is equal to 820 Newton meters. And so solving for t, 820 multiplied by 17 divided by 0.138 and divided by 3.3 gives me 30,600 newtons. And so I'll just divide that by 1,000 and I'll get 30.6 kilonewtons. That has to be a positive number because the tension in a rope has to be positive. I can't have a compressive force in a rope. And then all I have to do is just plug this number in for mz. Plug in the value of t. And so 30,000 times 0.138 divided by 9.4. Oops, divided by, no, not multiplied by 9.4 divided by 17 gives me 2,335 Newton meters. So just be careful here. When I plugged in t, I plugged in 30,600 so that I'd have the right units here. And so what I get is my moment in my z-axis is a bit larger than my moment in my x-axis. And if we had time in the exam, if we compare these two things, they're the same except for the moment arm. And so the ratio of the moment arms, 9.4 divided by 3.3, is about 2.84. And the ratio of the moments, 2335 divided by 820, is also 2.84. So it makes sense. I get the right ratio of my result moments.